Greetings, travelers. Have you ever wondered if we are alone? Tonight, on Deep Space Drifter, we explore that question through the lens of heat and light. We're talking about the Dyson Sphere. It is a concept of detection as much as construction, a way to find alien civilizations not by their radio songs, but by the warmth they leave behind. A Dyson Sphere is a star wrapped in industry, a sun dimmed by the machinery of a super civilization. Our narrative tonight takes us on a hunt for these techno-signatures. We will walk through the history of looking for infrared ghosts in the dark. We will learn how a physicist named Freeman Dyson taught us to search for waste heat, the inevitable exhaust of a star-spanning society. We will touch upon the solid shell fallacy, correcting the movies, and realize that we are looking for a swarm, not a shield. And finally, we will confront the silence, the great silence. If the universe is old and the physics are sound, where is everyone? But that is a question for the subconscious. For now, your only task is to rest. Find that perfect position where your body feels weightless. Let the tension drain out of your muscles like heat radiating into the night. Soften your gaze behind closed eyelids. The universe is vast and quiet, and tonight you are part of that quiet. Snuggle in deep. The search begins now. Chapter 1. Genesis of a Megastructure. The void between stars is not empty. It is saturated with ghosts, echoes of possibilities that never were. Blueprints sketched in the minds of dreamers, long returned to dust. Among these phantoms drifts the most persistent vision of all. A shell of engineered matter embracing a sun. A civilization's hunger for energy made manifest in orbital geometry. To trace the origin of this vision is not to follow an equation backward through time, but to descend into the fertile darkness of human imagination itself, a realm where science and speculation first learned to dance, long before radio telescopes scanned the heavens for anomalous infrared signatures, before Freeman Dyson formalized thermodynamic constraints into a search protocol for alien engineering. The seed was planted not in a laboratory, but in the quiet solitude of a writer's study. The year was 1937. Europe teetered on the brink of cataclysm. Yet, in a modest English home, philosopher Olaf Stapledon completed a manuscript that would quietly rewire the cosmic ambitions of generations to come. Star Maker was not a novel in any conventional sense. It was a metaphysical voyage spanning billions of years and countless galaxies, narrated by a consciousness flung beyond the confines of individual identity into communion with the universe's architect. Within its pages, Stapledon described not spaceships or ray guns, but civilizations that had transcended planetary existence through sheer scale of thought. He wrote of artificial atmospheres of gauze-like matter, vast networks of light-trapping structures woven around stars, not as solid shells, but as delicate, dynamic swarms harvesting photons with the precision of photosynthetic organisms scaled to stellar proportions. This was the true genesis, not an engineering proposal, but a philosophical proposition. That intelligence, given sufficient time and will, would inevitably seek to command the fundamental currency of the cosmos energy. Stapledon understood thermodynamics intuitively. Life is a localized defiance of entropy, a temporary eddy in the universal current toward disorder. To persist, to grow, to think ever more complex thoughts requires ever greater energy throughput. A planet offers a finite reservoir. A star offers a torrent. The leap from planetary to stellar civilization was not merely technological. It was biological destiny made manifest through engineering. Yet Stapledon himself stood upon earlier shoulders. Decades before Starmaker, Russian rocket pioneer Konstantin Tsiolkovsky had already begun sketching humanity's escape from Earth's gravitational well. Confined to a provincial schoolteacher's life, Tsiolkovsky dreamed in equations and thought experiments. He calculated escape velocities, envisioned liquid-fueled rockets, and proposed orbiting habitats where humans might live beyond the biosphere. His 1911 essay, The Will of the Universe, contained a startling prescience. Earth is the cradle of humanity, but one cannot live in the cradle forever. For Tsiolkovsky, space colonization was not adventure, it was evolutionary necessity. His artificial worlds were modest by later standards, rotating cylinders generating artificial gravity through centrifugal force, positioned in stable orbits where sunlight could be harvested through vast mirrors. But the conceptual bridge was built. Humanity's future lay not in conquering new continents, but in constructing new worlds from raw orbital mechanics. These literary and theoretical seeds found fertile ground in an unexpected demographic. The physicists who came of age between the world wars. They devoured science fiction not as escapism, but as cognitive training grounds for thinking at cosmic scales. The generation that would split the atom and decode stellar nucleosynthesis had first practiced their cosmic imagination on the pages of Amazing Stories, and Astounding Science Fiction They learned to hold in their minds concepts that defied terrestrial intuition. Time dilation near massive objects, the curvature of spacetime, the possibility that intelligence might not be a rare accident, but a cosmic imperative. When Freeman Dyson sat down in 1960 to write his seminal one-page paper for the journal Science, he was not inventing a concept from whole cloth. He was translating a literary vision into the rigorous language of thermodynamics and observational astronomy. The critical insight Dyson contributed was not how to build such a structure, but how to detect its thermodynamic signature. He recognized that any civilization capturing a star's visible light output must, by the unbreakable laws of energy conservation, re-radiate that energy as waste heat in the infrared spectrum. A star partially or fully enclosed by energy harvesting structures would appear anomalously dim in visible light, yet blazingly bright in infrared, a cosmic anomaly detectable across interstellar distances. Dyson was not proposing a solid shell. He explicitly described a loose collection or swarm of objects traveling on independent orbits, a cloud of solar collectors numbering in the billions. The physics was unequivocal. A rigid shell surrounding a star is dynamically impossible. Gravitational forces would be catastrophic. The shell would experience no net gravitational attraction to the star at its center, making orbital mechanics irrelevant, while any slight perturbation would cause it to drift until stellar plasma vaporized the structure. Furthermore, the compressive forces on such a shell would exceed the tensile strength of any known material by many orders of magnitude. The solid Dyson Sphere was always a fantasy, a compelling visual metaphor that would later dominate popular culture, but never a serious engineering proposal. The documentary vessel Odyssey, a long-range research craft stationed at the gravitational lensing point beyond Neptune's orbit, maintains a silent vigil over archival transmissions from Earth's past. Its crew, historians, astrophysicists, and exobiologists, have spent years compiling the intellectual lineage of megastructure concepts. Through quantum-stored light echoes and reconstructed electromagnetic signals, they have assembled a chronology of human cosmic ambition. The captain oversees data streams showing how Stapledon's gauze of light traps evolved in the public imagination. First, through John W. Campbell's editorial influence on 1940s science fiction. Then, through the Cold War-era fascination with total energy systems, culminating in Dyson's formalization at the dawn of the space age. The vessel's sensors sweep the galactic plane, not yet searching for actual megastructures, but calibrating detection algorithms against known astrophysical phenomena. Each anomalous infrared source, cataloged by the WISE telescope, is cross-referenced against the historical record of human speculation. The crew understands that before one can recognize an alien artifact, one must first understand the full spectrum of natural phenomena that might mimic it: circumstellar dust clouds, protoplanetary disks, brown dwarfs shrouded in debris. They study the light curves of young stellar objects exhibiting irregular dimming, learning to distinguish between the chaotic signatures of natural accretion disks and the mathematically precise shadows that might betray artificial geometry. This preparatory work is itself a form of archaeology, excavating the boundary between natural and artificial in a universe that has, thus far, revealed only the former. What the crew discovers in their archival work is that the Dyson concept emerged precisely when humanity first grasped its own thermodynamic predicament. The 1950s and 60s saw the convergence of three realizations. First, that nuclear fusion powered stars for billions of years. Second, that Earth's fossil fuel reserves were finite on civilizational timescales. Third, that radio astronomy had opened a new window on the universe. Dyson's paper appeared in 1960, the same year Frank Drake formulated his equation for estimating the number of detectable civilizations in the galaxy. These were not coincidences. They represented a species awakening to its place in a cosmic energy economy. For the first time, humans could conceive of energy budgets measured not in kilowatt hours, but in stellar luminosities. The sun outputs approximately 3.8 times 1026 watts, a number so vast it defies intuitive comprehension. Yet Dyson recognized that exponential growth, even at modest rates, would inevitably drive any persistent civilization toward such scales. A society growing its energy consumption by just 1% annually would require the total output of its star within 3 millennia. This was not science fiction. It was compound interest applied to thermodynamics. The vessel's chief astrophysicist directs attention to archival footage of early space missions, Sputnik's metallic beep echoing through the ionosphere, Apollo astronauts planting flags in lunar regolith. These were not merely political gestures. They were humanity's first tentative steps toward becoming a multibody species, a prerequisite for any civilization aspiring to stellar engineering. Before one can dismantle Mercury for raw materials, one must first master orbital mechanics around one's home planet. Before deploying self-replicating von Neumann probes to disassemble worlds, one must first land a rover on Mars. The progression is thermodynamic inevitability made manifest through incremental engineering. As the Odyssey completes its archival survey, its long-range sensors detect a faint infrared anomaly in the Cygnus arm, a star exhibiting a 15% dip in visible luminosity with a corresponding infrared excess. The crew does not celebrate. They initiate protocol, spectral analysis to determine dust composition, multi-wavelength observation to rule out instrumental artifacts, comparison against catalogs of known variable stars and debris disks. The anomaly will likely resolve into natural phenomena, perhaps a swarm of comets perturbed by a passing star, or a young star still clearing its protoplanetary disk. But the procedure itself is significant. Humanity has built the conceptual framework to recognize its own speculative fiction made real. We have learned to see the universe not just as it is, but as it might be engineered. The chapter closes with the vessel turning its instruments toward the galactic center, where ancient stars burn in dense clusters. The crew understands that if Dyson swarms exist anywhere, they are most likely found there, around long-lived K and M-dwarf stars, where civilizations might have had billions of years to evolve towards stellar-scale engineering. But the sensors register only the expected thermal signatures of natural objects. The sky remains silent, yet in that silence lies a profound truth. The mere fact that we can conceive of enclosing stars, that we can calculate the infrared signatures of hypothetical alien engineering, that we can distinguish between natural dust clouds and potential artifacts, that capacity itself marks a threshold crossed. We have moved from being passive inhabitants of a cosmic habitat to becoming conscious participants in the universe's thermodynamic narrative. The first chapter of stellar engineering was not written in steel or silicon, but in ink and imagination. The blueprint existed in Stapledon's prose before it existed in Dyson's equations. And somewhere, perhaps, another consciousness in another galaxy followed the same path from literary speculation to thermodynamic necessity, until the stars themselves began to dim at their command. The search continues not because we expect to find them tomorrow, but because the act of searching transforms us into the kind of species that might one day build such wonders ourselves. The cradle door has been opened. Whether we step through remains the unwritten next chapter. Chapter 2, the thermodynamic signature. The year 1960 arrived draped in the twin mantles of terror and transcendence. Humanity stood poised between annihilation and apotheosis, its fingers simultaneously clutching the triggers of thermonuclear arsenals and the controls of rockets piercing the ionosphere. Sputnik's metallic chirp still echoed in the collective memory, a stark announcement that the heavens were no longer sanctuary, but territory. In this crucible of Cold War anxiety and cosmic ambition, a theoretical physicist at the Institute for Advanced Study in Princeton performed an act of profound intellectual alchemy. He transformed a literary fantasy into a testable hypothesis about the universe. Freeman Dyson did not set out to design a star-faring civilization's power grid. He sought only to expand the vocabulary of cosmic detection, to teach humanity how to recognize intelligence, not by its messages, but by its thermodynamic footprint. Dyson's paper, published in the June 3, 1960 issue of the journal Science, occupied precisely one typeset page. Its title betrayed its methodological purpose. search for artificial stellar sources of infrared radiation. The brevity was deliberate, almost dismissive of the cultural earthquake it would trigger. Within this compact framework, Dyson performed a masterful application of the first and second laws of thermodynamics to astrobiology. Energy cannot be created or destroyed. It can only change form. Any civilization capturing electromagnetic radiation from its host star must eventually re-radiate that energy as waste heat. And because the collectors would operate at temperatures far cooler than the stellar photosphere, perhaps a few hundred Kelvin rather than thousands, the re-radiated energy would shift from visible wavelengths into the infrared spectrum. This was not speculation. It was thermodynamic inevitability. A star partially enclosed by energy harvesting structures would exhibit a spectral anomaly. Diminished luminosity in the optical band, paired with excess emission in the mid-infrared range, around 10 micrometers. The signature would be unmistakable to instruments capable of measuring it. The elegance of Dyson's approach lay in its inversion of SETI's founding premise. Just months earlier, Frank Drake had conducted Project Ozma, pointing a radio telescope at Tau Ceti and Epsilon Eridani to listen for deliberate transmissions. Dyson proposed a radically different search strategy. Look not for signals intentionally broadcast, but for the unavoidable waste products of cosmic scale engineering. A civilization might choose not to communicate. It could not choose to violate the conservation of energy. The infrared excess would betray its existence as surely as smoke betrays fire. This reframing elevated the search for extraterrestrial intelligence from the domain of linguistics and cryptography into the realm of observational astrophysics. One no longer needed to decode alien languages. One needed only to recognize anomalous thermal profiles against the backdrop of natural stellar populations. The documentary vessel Odyssey, having completed its archival survey of Stapledon's literary influence, now directs its quantum memory banks toward the historical moment of formalization. Its crew of astrophysicists and historians reconstructs the intellectual climate of 1960 through preserved electromagnetic records. They observe how Dyson's thinking emerged from a confluence of three parallel developments: the maturation of radio astronomy, the emerging understanding of stellar nucleosynthesis, and the first serious calculations regarding exponential growth in energy consumption. Dyson had participated in Project Orion, the audacious study of spacecraft propulsion via nuclear pulse detonations, and understood viscerally that civilizations operating at planetary scales would inevitably confront energy constraints. He recognized that exponential growth, even at modest annual rates, produces staggering demands over geological timescales. a society increasing its energy use by merely 1% per year would require the entire output of its star within 3,000 years. This was not science fiction. It was compound interest meeting thermodynamics. Critically, Dyson never proposed a solid shell. His paper explicitly described a very large number of small objects in independent orbits, a swarm of solar collectors, habitats, and energy relays numbering in the billions. He understood orbital mechanics too well to suggest a rigid sphere. Such a structure would experience no net gravitational attraction to the central star. Gravity inside a uniform spherical shell cancels to zero by Newton's shell theorem. Without active station-keeping propulsion beyond any foreseeable technology, the slightest perturbation would cause the shell to drift until contact with the stellar corona vaporized it. Furthermore, the compressive stresses on a solid shell would exceed the yield strength of any known material by many orders of magnitude. The physics was unequivocal. A rigid Dyson sphere was dynamically impossible. Dyson's proposal was deliberately modest, almost conservative, a natural extension of humanity's own nascent satellite programs scaled to stellar proportions. The Odyssey as chief historian isolates archival footage of early satellite deployments. Vanguard 1's 6-inch aluminum sphere circling Earth in 1958. Explorer 1's cosmic ray detectors mapping the Van Allen belts. These primitive objects represented the embryonic stage of what Dyson envisioned, a cloud of artificial bodies harvesting energy from their star. The progression from Vanguard to a Dyson Swarm was not a leap of imagination, but a continuum of scale. Each satellite represented a node in an expanding network of orbital infrastructure. Given sufficient time, replication capability, and resource access, such networks could grow to encompass their entire stellar system. The vessel's sensors simulate this growth algorithmically, starting with a single collector at Mercury's orbit, introducing self-replication with a doubling time of 1 year. The swarm achieves partial stellar occlusion within 4 centuries. The simulation does not depict construction. It depicts colonization, the gradual conversion of inert matter into energy-harvesting structures through exponential replication. This brings the crew to Dyson's most profound insight: the distinction between engineering feasibility and thermodynamic inevitability. He was not asking whether humanity could build such a structure in the 21st century. He was asking whether any persistent intelligence, given millions of years of stable development, would inevitably evolve toward stellar-scale energy harvesting. The answer, he argued, lay in biology itself. Life is a dissipative structure, a localized eddy resisting entropy's universal current. To maintain complexity, to evolve greater intelligence, to sustain larger populations, requires ever-increasing energy throughput. Planetary resources, geothermal vents, fossil fuels, wind, hydroelectric potential represent finite reservoirs on civilizational timescales. A star offers a continuous torrent. The sun outputs 3.8 times 10^26 watts, equivalent to detonating 100 billion megatons of TNT every second. For a species measuring its energy budget in terawatts, this represented not merely abundance, but transcendence. The vessel's thermal imagers calibrate against historical infrared surveys, tracing the lineage from Dyson's 1960 proposal to the infrared astronomical satellite, IRAS, launched in 1983. Then to the Wide Field Infrared Survey Explorer, WISE, mission of 2009. Each instrument represented a technological fulfillment of Dyson's methodological prescription. The crew analyzes spectral energy distributions of thousands of cataloged stars, training detection algorithms to distinguish between natural infrared sources, protostellar disks, asymptotic giant branch stars shrouded in dust, and potential artificial signatures. They learn that nature is prolifically inventive in mimicking Dyson's predicted anomalies. Young stellar objects surrounded by accretion disks exhibit precisely the combination of optical dimming and infrared excess that would flag a partial Dyson swarm. Circumstellar debris disks around main sequence stars produce similar signatures. The challenge was not detecting infrared excess. It was discriminating artificial geometry from natural chaos. This discrimination requires examining not just spectral signatures, but temporal behavior. Natural dust clouds produce irregular, asymmetric dimming events as clumps pass before a star. A partially constructed Dyson swarm would generate mathematically precise transit signatures, repeating geometric patterns reflecting orbital resonances among collector arrays. The asterisk Odyssey asterisk S astrometric sensors practice this discrimination on known variable stars, building a library of natural light curve morphologies against which future anomalies might be compared. The crew understands that Dyson's true legacy was not a blueprint, but a filter, a conceptual sieve for separating cosmic noise from potential technosignatures. The documentary vessel now turns its instruments toward the historical record of Dyson's reception. Initial responses were muted. The paper was regarded as an intriguing thought experiment rather than a serious observational program. Astronomers lacked the infrared instrumentation to conduct systematic surveys. The concept simmered in academic circles for 2 decades before technology caught up with theory. When IRAS scanned the entire sky in 4 infrared bands between 1983 and 1984, it detected over 350,000 infrared sources. Follow-up observations revealed all to be natural phenomena: dust-shrouded stars, galactic nuclei, interstellar clouds. No Dyson swarms. Yet the search had begun in earnest. Dyson had provided astronomy with a new category of object to seek, a new way of seeing the cosmos, not as a collection of natural phenomena alone, but as a potential repository of engineering. The *Odyssey S captain reviews the thermodynamic calculations that underpin the entire search paradigm. Each watt of stellar radiation captured must eventually be re-radiated. If a civilization uses that energy for computation, the waste heat emerges as infrared photons. If it powers habitats, the heat radiates from habitat surfaces. If it drives propulsion systems, the exhaust plumes glow in infrared. There is no escape from this accounting. The universe maintains perfect books. This realization transforms the search for extraterrestrial intelligence from a gamble on alien psychology, will they communicate, into a certainty of physics, must they radiate. The former question might have no answer. The latter has only one: yes. As the vessel completes its analysis of the 1960 formalization period, its sensors detect a faint infrared source in the constellation Cygnus, exhibiting a 22% optical dimming with corresponding mid-infrared excess. Protocol initiates automatically. Spectral decomposition to identify silicate absorption, features characteristic of cosmic dust. Multi-epoch photometry to determine transit periodicity. Comparison against the Odyssey S catalog of 14,387 natural variable stars. Within 17 minutes, the anomaly is classified as a young stellar object with a warped inner disk, natural, not artificial. The crew does not register disappointment. They register refinement. Each false positive sharpens the discrimination algorithms, narrows the parameter space, brings the detection threshold closer to reality. The search is not a hunt for a single smoking gun. It is the gradual construction of a cosmic census that distinguishes nature's repertoire from engineering's signature. The chapter closes with the vessel's long-range sensors sweeping the galactic plane, measuring infrared backgrounds against theoretical models of a galaxy populated by type II civilizations. The observed background matches predictions for natural sources alone. The sky remains thermodynamically quiet. Yet, in that quiet lies profound significance. Dyson taught humanity to listen not with radio dishes tuned to specific frequencies, but with bolometers measuring the universe's heat budget. He transformed a science fiction trope into an observational discipline. The solid shell of popular imagination remained fantasy, but the infrared signature, the unavoidable thermodynamic confession of a star-harvesting civilization, became a legitimate target for astronomical inquiry. Before one can recognize an alien artifact, one must first conceive of its physical signature. Dyson provided that conception. He did not tell us how to build a sphere around a star. He taught us how to see the shadow such a structure would cast upon the cosmos, not in visible light, but in the gentle, inescapable glow of waste heat radiating into the interstellar void. The search had acquired its methodology. The next step would be patience, instrumentation, and the slow, meticulous sifting of starlight for the fingerprints of cosmic engineering. Chapter 3: The Solid Shell Fallacy. The human mind craves symmetry. It seeks closure in geometry, elegance in simplicity, and narrative satisfaction in singular, monumental forms. When Freeman Dyson's 1960 paper entered the cultural bloodstream, it encountered not the careful scrutiny of peer review, but the distorting lens of visual imagination. Within decades, a subtle but catastrophic mutation occurred. The physicist's swarm of independent collectors, the only configuration permitted by orbital mechanics, was transmuted in the public consciousness into a single, seamless shell of impossibly strong material, encasing a star like a jewel in a setting. This transformation was not born of scientific illiteracy alone, but of a deeper aesthetic imperative. The solid shell made for better cinema. Its clean lines, its architectural grandeur, its visceral comprehensibility. It was a monument scaled to stellar proportions, and humanity, a species of monument builders, could not resist the image. The documentary Vessel Odyssey, having completed its analysis of Dyson's original thermodynamic framework, now turns its archival sensors toward the cultural metamorphosis of the concept. Its crew of historians and physicists trace the mutation through preserved media streams, observing how scientific nuance dissolved into visual spectacle. The critical inflection point arrived not in a laboratory, but in the pages of science fiction magazines and the storyboards of television studios. Larry Niven's 1970 novel, Ringworld, presented a rotating band of habitable material encircling a star at planetary distance, a structure already straining the limits of material science, yet possessing a certain geometric purity that captivated readers. Though Niven's creation was explicitly a ring rather than a sphere, the visual vocabulary of stellar scale engineering had been established. Rigid, monolithic, architecturally intentional. The public mind conflated the two concepts, absorbing the aesthetic of engineered stars without distinguishing their physical plausibility. Television completed the transformation. In 1992, Star Trek: The Next Generation aired the episode Relics, featuring the Asterisk Enterprise discovering a fully enclosed Dyson Sphere with an inhabited interior surface and a single access portal. The visual was unforgettable. A star contained within a perfect geometric shell, its light diffused across an artificial sky for billions of inhabitants. The episode made no attempt to address the physics of such a structure. It served narrative and visual purposes alone. Yet, for millions of viewers, this became the definitive image of a Dyson sphere, a solid shell, habitable on its inner surface, stable and eternal. The mutation was complete. Dyson's swarm of independent collectors, invisible from interstellar distances except through their collective infrared signature, had been replaced in the popular imagination by a single, photographable megastructure. The scientifically plausible had been sacrificed to the cinematically spectacular. The Asterisk Odyssey Asterisk S structural engineering module now initiates a systematic demolition of the solid shell concept, applying fundamental physical laws to expose its impossibility. The first and most decisive refutation arrives from Newtonian gravity itself. Newton's shell theorem, derived in the Principia Mathematica of 1687, demonstrates that a uniform spherical shell exerts no net gravitational force on objects inside it. For a hypothetical solid Dyson shell, this means the star at its center would experience zero gravitational attraction to the shell surrounding it. The shell would not orbit the star. Orbital mechanics would be irrelevant. Without active station-keeping thrusters of unimaginable power operating continuously across its entire surface, the slightest perturbation, a passing comet's gravity, a solar flare's momentum transfer, even the asymmetric radiation pressure of the star itself would cause the shell to drift. Within years, perhaps decades, the shell would contact the stellar photosphere. At temperatures exceeding 5,000 Kelvin for a sun-like star, the structure would vaporize instantly. Stability was not merely difficult. It was dynamically forbidden by the inverse square law that governs the cosmos. The crew's materials science database then calculates the mechanical stresses inherent in such a structure. A shell positioned at Earth's orbital distance, approximately 150 million kilometers from its star, would need to withstand not gravitational attraction to the star, which, per Newton's theorem, would be zero, but the colossal compressive forces generated by its own rotation. To simulate Earth-like gravity on its inner surface, the shell would need to rotate once every 9 days. This rotation would generate centrifugal forces attempting to fling the structure apart. The resulting tensile stress at the shell's equator would exceed 1018 pascals, approximately 1 billion times the tensile strength of diamond, the strongest naturally occurring material. Even theoretical materials like carbon nanotubes or graphene monolayers, with tensile strengths approaching 1011 pascals, fall short by 7 orders of magnitude. No arrangement of atomic bonds, no crystalline lattice, however perfect, could resist forces that would tear apart the very electromagnetic interactions holding matter together. The shell would not merely crack, it would disintegrate into a cloud of plasma before achieving even a fraction of its required rotational velocity. Further analysis reveals additional fatal flaws. A solid shell would possess no mechanism for thermal regulation. The star's radiation, absorbed by the inner surface, would heat the structure until it glowed at equilibrium temperature, approximately 300 Kelvin for Earth orbit distance. But this heat could not be efficiently radiated away. The outer surface, facing the cold of interstellar space, would indeed emit infrared radiation. However, the thermal conductivity required to transfer heat from the inner to outer surface across a structure, potentially kilometers thick, would demand materials with thermal properties exceeding any known substance by orders of magnitude. Localized hot spots would develop, creating thermal stresses that would fracture the shell long before global equilibrium was achieved. Meanwhile, the shell would present an enormous cross-section to micrometeorite impacts. At interstellar velocities, even dust grains carry kinetic energy equivalent to nuclear detonations relative to their mass. A solid shell would require continuous planet-scale repair operations just to maintain integrity against the gentle rain of interstellar debris, a maintenance burden exceeding the construction effort itself. The vessel's historical archives isolate Freeman Dyson's own reactions to this cultural distortion. In interviews preserved in electromagnetic records from the 1990s and early 2000s, Dyson expresses not anger, but ripe amusement at his name becoming attached to an engineering impossibility he never proposed. He repeatedly clarifies that his 1960 paper described a loose collection or swarm of objects traveling on independent orbits, explicitly rejecting the solid shell as mechanically impossible. Yet he also acknowledges the power of the image. The solid sphere is a wonderful symbol, he concedes in one recording. It represents the ambition of intelligence to reshape its environment on the largest possible scale. As poetry, it succeeds brilliantly. As engineering, it fails catastrophically. This tension between poetic resonance and physical plausibility defines the Dyson Sphere's cultural journey, a concept born in thermodynamics, refined in orbital mechanics, and reborn in the collective imagination as something more beautiful and more impossible than its originator ever intended. The Odyssey S crew recognizes that this mutation was not merely an error, but a necessary step in the concept's cultural transmission. Human cognition evolved to navigate environments at human scales meters, not astronomical units seconds, not millennia. A swarm of billions of independent collectors, each following its own Keplerian orbit, defies intuitive comprehension. It has no single shape, no unified form, no photographable moment of completion. It is a process, not a monument. The solid shell, by contrast, maps cleanly onto human experience. It is a container, a vessel, a world turned inside out. It satisfies our innate preference for bounded spaces, for horizons that close upon themselves. The mutation was not a failure of science communication, but a triumph of cognitive accessibility, a simplification so powerful it overwrote the original concept in the public mind. Yet this simplification carries consequences beyond aesthetics. The Odyssey S astrophysics module demonstrates how the solid shell misconception has distorted public understanding of the search for extraterrestrial intelligence. When anomalies like KIC 8,462,852 tabbies star exhibited irregular dimming in 2015, media coverage fixated on the image of a partially constructed solid shell, with gaps allowing starlight to leak through. This framing misled the public about what astronomers were actually seeking, not geometric gaps in an impossible structure, but the statistical signature of a cloud of independent objects producing non-periodic, asymmetric transits. The solid shell myth created expectations of clean, architectural shadows rather than the messy, probabilistic dimming patterns expected from a true Dyson Swarm. Science communication suffered because the public's mental model of the phenomenon was fundamentally misaligned with physical reality. The vessel now conducts a comparative analysis of fictional megastructures to isolate why the solid shell proved so culturally persistent. Niven's Ringworld, while physically implausible, at least possessed internal consistency. It rotated for artificial gravity, employed attitude jets for stability, and acknowledged material science limitations through the invention of Skrith, an impossibly strong fictional material. The solid Dyson shell made no such concessions to plausibility. It simply existed as a given, its stability assumed rather than explained. Yet its spherical symmetry gave it a primal appeal that the ring's linear geometry lacked. The sphere is the universe's preferred shape for self-gravitating bodies, stars, planets, moons, all formed by the isotropic pull of gravity. A solid shell around a star completes this cosmic symmetry. Sphere within sphere, perfection enclosing perfection. This aesthetic resonance overpowered physical objections in the cultural imagination. As the Odyssey completes its analysis of the misconception's origins and consequences, its sensors detect a pattern in humanity's megastructure fantasies. They consistently prioritize visual comprehensibility over physical plausibility. From Bernal spheres to O'Neill cylinders to the solid Dyson shell, the most enduring concepts are those that can be rendered in a single, striking illustration. This reveals a profound truth about scientific imagination. It is constrained not only by physical law, but by cognitive architecture. We conceive of the possible through the lens of the imaginable, and the imaginable is bounded by evolutionary history. A species that evolved navigating three-dimensional spaces with clear boundaries will naturally imagine cosmic engineering as bounded spaces scaled upward. The swarm, the distributed, non-hierarchical, process-oriented reality of stellar-scale energy harvesting, resists this cognitive mapping. It has no face, no front door, no single moment of completion. It is civilization as ecosystem rather than architecture. The chapter closes with the vessel's captain reviewing Dyson's original paper one final time, its single page glowing in the quantum display. The text remains unchanged by decades of cultural distortion. A very large number of small objects. The physics remains unchanged as well. Newton's shell theorem still holds. Material strength limits still bind. Thermodynamics still demands infrared re-radiation. The solid shell exists only in the space between human desire and physical law, a beautiful impossibility that teaches us as much about ourselves as about the cosmos. It reveals our longing for monuments that outlast stars, our craving for order imposed upon chaos, our refusal to accept that the most profound cosmic engineering might be invisible except through its thermal signature, a whisper of waste heat against the cold void. The misconception, then, serves a purpose beyond error correction. It functions as a mirror reflecting humanity's relationship with scale itself. We struggle to conceive of projects spanning millennia, of intelligence distributed across billions of autonomous units, of engineering that never reaches completion because completion is not the goal, continuous expansion is. The solid shell comforts us with the illusion of finitude, a project with a beginning, middle, and end. The swarm confronts us with the reality of cosmic scale endeavors. They are processes without terminus, evolutions without final form. To accept the swarm is to accept that the universe's grandest works may lack the satisfying closure of human architecture. They may be messy, distributed, and perpetually incomplete, like life itself. The asterisk Odyssey turns its sensors away from Earth's cultural archives and back toward the starfields. The solid shell remains a phantom, a ghost in the machine of human imagination. But in exorcising this phantom, by understanding its origins, its appeal, and its impossibility, the crew has cleared conceptual space for what might actually exist out there. Not monuments, but metabolisms, not shells, but swarms, not static structures, but dynamic equilibria between stars and the intelligence that learns to drink their light. The search continues, now informed by both thermodynamic rigor and cultural self-awareness. The sky remains silent, but the silence is no longer misinterpreted. We listen not for the shadow of an impossible shell, but for the gentle, inescapable warmth of a civilization that has learned to live not inside a sphere, but within the mathematics of orbital mechanics itself. Chapter 4: The Architecture of Patience. The dismantling of a world begins not with explosions, but with mathematics. Before the first robotic miner touches regolith, before the first solar collector unfurls in the void, the project exists as a series of conservation equations, mass budgets, energy flows, orbital resonances, calculated to 6 decimal places. The documentary vessel Odyssey, having dispelled the myth of the solid shell, now turns its analytical sensors toward the only physically permissible architecture for stellar scale engineering: the Dyson Swarm. This is not a structure in the conventional sense. It is a process, a slow, deliberate conversion of inert planetary matter into orbiting energy harvesting infrastructure, unfolding across millennia with the inevitability of geological epochs. The crew's astrophysics module initiates mass balance calculations to determine the raw material requirements. A swarm capable of capturing even 10% of a sun-like star's output, approximately 4 times 10^25 watts, requires collectors with a combined surface area exceeding 2.7 times 10^15 square kilometers. Assuming collectors fabricated from aluminum or silicon, substrates 1 millimeter thick, the mass requirement approaches 10^24 kilograms. Earth's entire crust contains only 2.5 times 10^22 kilograms of accessible material, insufficient by 2 orders of magnitude. The inner solar system must be mined systematically. Mercury, with its iron-rich core and proximity to the sun, presents the optimal first target. Its total mass of 3.3 times 10^23 kilograms could supply collectors capturing nearly 40% of solar output. Venus and the asteroid belt would provide additional reservoirs. The mathematics is unambiguous. Stellar engineering demands planetary sacrifice. Worlds become not destinations, but quarries. The vessel's historical archives isolate the theoretical foundation for this conversion process. John von Neumann's 1940s work on self-replicating automata. Von Neumann demonstrated mathematically that a machine capable of constructing copies of itself from raw materials could achieve exponential growth. Applied to stellar engineering, this principle transforms construction from linear labor into a geometric cascade. The Cruise simulation module models the deployment sequence. Phase 1. A single seed probe massing 10 tons lands on Mercury's surface. Using concentrated solar energy to melt regolith, it fabricates photovoltaic cells, structural struts, and propulsion systems from locally mined silicon, iron, and aluminum. Within 18 months, it assembles 2 functional copies of itself. Phase 2. 3 probes become 6, then 12, then 24. The doubling time stabilizes at approximately 1 year as resource extraction infrastructure scales. Within 32 doublings, just over 3 decades, the swarm of miners numbers 4.3 billion units, each operating autonomously across Mercury's surface. Phase 3 commences as mining transitions to launch operations. Electromagnetic mass drivers, kilometers in length, accelerate refined material packets into solar orbit at precisely calculated velocities. Each packet contains prefabricated collector components that self-assemble upon reaching designated orbital slots. The swarm does not form a uniform shell. Orbital mechanics forbids it. Instead, collectors distribute across multiple orbital planes and distances, forming a complex 3-dimensional cloud with density gradients optimized for energy capture while minimizing collision probabilities. At Mercury's orbit, 0.4 astronomical units, collectors complete orbits every 88 days. At Earth's distance, 1 AU, the period extends to 365 days. At Mars' orbit, 1.5 AU, nearly 2 Earth years elapse per revolution. The resulting structure is a dynamic ballet of independent objects, no 2 sharing identical trajectories, their collective shadow falling upon the star in ever-shifting patterns. The Asterisk Odyssey, Asterisk S engineering module, now models collision avoidance protocols essential for swarm stability. With billions of objects occupying the inner solar system, the probability of catastrophic impacts would approach certainty without active management. Each collector incorporates millimeter-scale thrusters powered by its own photovoltaic output, enabling micro-adjustments to orbital parameters. Machine learning algorithms predict conjunction events decades in advance, calculating minimal energy maneuvers to maintain safe separation distances. The system operates as a distributed intelligence, no central controller directing traffic, but emergent order arising from simple local rules encoded in each unit's firmware. This architecture mirrors natural systems, flocks of birds, schools of fish, the orbital resonances of Jupiter's moons. Complexity without centralization, order without command. Alternative architectures emerge from the same thermodynamic imperative, but different engineering philosophies. The Dyson bubble represents the most elegant solution to orbital mechanics constraints. Instead of orbiting collectors, this design employs statites, static satellites held in position not by velocity, but by radiation pressure. Ultra-thin solar sails, mere micrometers thick and kilometers in diameter, balance the inward pull of gravity against the outward push of stellar photons. At Earth's orbital distance, a sail with a mass-to-area ratio below 0.75 grams per square meter achieves equilibrium. Advanced metamaterials, graphene monolayers, carbon nanotube meshes approach this threshold. Statites require no orbital velocity, eliminating collision risks inherent in swarms. They can position themselves at optimal angles for energy collection or transmission. Yet they demand material science at the edge of physical possibility and remain vulnerable to solar wind perturbations during coronal mass ejections. The bubble is theoretically superior, but technologically more demanding than the swarm. The vessel's temporal analysis module compresses millennia into comprehensible narrative. Construction does not proceed as a single project with a completion date. It unfolds as a phase transition in the solar system's material state, from gravitationally bound planets to distributed energy infrastructure. Year 0. Seed probe launch from Earth orbit. Year 35. Mercury's surface transformed into a fractal landscape of mining pits and mass drivers. Year 120. First gigawatt-scale power transmission to Earth via microwave beams, supplementing terrestrial grids. Year 287. Mercury fully disassembled, its mass redistributed as 10-12 collectors, forming a partial swarm. Year 643. Venus begins atmospheric stripping to access its metallic core. Year 1892. Swarm density reaches 50% stellar occlusion. Earth's climate engineers deploy orbital mirrors to compensate for reduced insolation. Year 3417. Asteroid belt mining operations commence, expanding swarm radius to Jupiter's orbit. Year 8904. 95% of solar output captured. The sun appears as a diffuse glow behind a cloud of collectors when viewed from interstellar distances. Throughout this timeline, no single generation witnesses completion. The project transcends individual lifespans, requiring cultural continuity mechanisms more robust than any previous human endeavor. The crew's sociology database identifies necessary conditions: stable planetary governance capable of maintaining multimillennial projects, economic systems that value intergenerational investment over quarterly returns, educational institutions that transmit technical knowledge across centuries without degradation. Historical precedents exist on miniature scales: the medieval cathedrals whose builders never saw completion, the Svalbard Global Seed Vault designed to outlast civilizations. But nothing approaches the temporal scope of stellar engineering. The Dyson Swarm is not built, it grows. Like a coral reef or a forest, it emerges from countless individual actions aligned toward a collective outcome no single actor will witness. The vessel now directs its sensors toward energy transmission mechanics, the critical link between capture and utilization. Photons absorbed by swarm collectors convert to electricity, which powers microwave or laser transmitters, beaming energy to receiving stations. Physics imposes hard constraints. Diffraction limits beam spread. A microwave transmitter 1 kilometer in diameter, operating at 10 gigahertz, spreads to approximately 100 kilometers wide at Earth's distance, requiring correspondingly large retina arrays for efficient reception. Laser systems achieve tighter focus, but suffer atmospheric absorption losses. The optimal solution emerges as a hybrid architecture: microwave transmission for planetary surface delivery, laser links for deep space propulsion and orbital habitats. Each collector dedicates 15% of its output to station-keeping propulsion and transmission systems, 85% to the energy grid. Thermodynamics demands waste heat dissipation. Collectors radiate excess heat as infrared photons at temperatures between 300 and 400 Kelvin, creating the signature Dyson predicted: a star dimmed in visible light, but blazing in the mid-infrared spectrum. The crew's materials science module examines the evolutionary trajectory of collector technology. First-generation units employ silicon photovoltaics with 15% efficiency, aluminum substrates, and chemical thrusters. Second-generation units, fabricated by the self-replicating Swarm itself, incorporate gallium arsenide cells, 30% efficiency, carbon fiber structures, and ion propulsion. Third generation units utilize quantum dot photovoltaics, approaching the Shockley-Queisser limit of 68% efficiency for single junction cells, graphene substrates, and photon thrusters. Each generation improves efficiency, reduces mass, and extends operational lifetime. The Swarm evolves not through deliberate redesign, but through competitive selection. Units with superior energy capture ratios replicate more rapidly. Their design parameters propagating through the population. Natural selection operates on machines. The swarm becomes not merely infrastructure, but an evolving technological ecosystem. As the Odyssey completes its architectural analysis, its sensors model the gravitational consequences of planetary disassembly. Mercury's removal alters the solar system's moment of inertia, perturbing the orbits of remaining planets by measurable but non-catastrophic amounts. Venus' eventual dismantling produces larger effects, requiring active orbital correction for Earth using asteroid gravity tractors, small bodies positioned to exert gentle gravitational tugs over centuries. The solar system transforms from a stable Newtonian clockwork into a managed environment requiring continuous adjustment. This represents a profound philosophical threshold. Humanity ceases being a passive passenger on a planet and becomes an active steward of orbital mechanics itself. The cosmos is no longer a given. It becomes a garden requiring cultivation. The chapter closes with the vessel's long-range sensors simulating the view from a passing interstellar probe. The sun no longer appears as a solitary point of light. It glows within a complex, asymmetric cloud of artificial objects denser near the ecliptic plane, thinner at the poles, with density fluctuations reflecting the swarm's ongoing growth. No solid shell encloses it. No geometric perfection announces artificiality to the casual observer. Only spectral analysis reveals the truth. Visible light diminished by 60%, infrared emission elevated by corresponding magnitude, the precise thermodynamic signature of intelligence harvesting stellar energy. The structure is invisible except through its thermal confession. It makes no statement. It performs no function beyond energy capture. It simply exists, as inevitable as photosynthesis, as patient as evolution, as vast as the orbital spaces it gradually fills. This is the reality of stellar engineering, not a monument to be admired, but a metabolism to be sustained. Not a single act of creation, but a continuous process of conversion, rock to circuit, planet to power grid, matter to energy flow. The solid shell was poetry. The swarm is physics. And physics, unlike poetry, makes no concessions to human aesthetics. It demands patience measured in millennia, sacrifice measured in worlds, and vision measured in light years. The blueprint exists not in architectural renderings, but in the equations of orbital mechanics and thermodynamics. The tools exist not in factories, but in the principles of self-replication and exponential growth. The timeline exists not in project schedules, but in the slow, inexorable mathematics of compound expansion. A civilization capable of conceiving this architecture has already taken the first step, not by launching a probe, but by accepting that the greatest works require timescales exceeding individual lifetimes. The dismantling of Mercury begins with a single equation solved in silence. Everything that follows is merely arithmetic. Chapter 5: The Energy Imperative. Civilizations do not expand for adventure. They expand for calories. This biological truth, governing everything from bacterial colonies to rainforest canopies, scales without alteration into the cosmic realm. Life is a dissipative structure, a localized defiance of entropy, sustained only by continuous energy throughput. To grow more complex, to sustain larger populations, to compute more sophisticated thoughts, requires ever greater power flows. The documentary Vessel Odyssey, having completed its architectural analysis of swarm construction, now directs its sensors toward the deeper question: why would any intelligence undertake a project spanning millennia and consuming entire worlds? The answer lies not in ambition alone, but in thermodynamics made manifest through sociology, a progression as inevitable as stellar evolution itself. In 1964, Soviet astronomer Nikolai Kardashev proposed a classification system that would reframe humanity's cosmic self-perception. Observing the exponential growth of radio astronomy capabilities, Kardashev recognized that energy consumption, not technology, not morality, not artistry, served as the only universal metric for comparing civilizations across interstellar distances. His scale was elegantly simple. A Type I civilization commands all energy resources available on its home planet, harnessing sunlight, wind, geothermal vents, and tidal forces to achieve a power budget on the order of 10-16 watts. A Type II civilization transcends planetary constraints to capture the total output of its host star, approximately 1026 watts for a sun-like star. A Type III civilization commands the energy of an entire galaxy, 10 watts or more, through networks of stellar engineering spanning spiral arms. Humanity's position on this scale reveals both our precariousness and our trajectory. Current global energy consumption hovers near 2 times 1013 watts, 3 orders of magnitude below planetary mastery. We remain a Type 0.7 civilization, still dependent on finite fossil reservoirs accumulated over geological epochs, still vulnerable to planetary scale disruptions we cannot control. Yet, our trajectory points unmistakably upward. Since the Industrial Revolution, human energy use has grown at approximately 2.3% annually, a rate that sustained would elevate us to Type I status within 2 centuries and Type II within 3 millennia. This is not speculation. It is compound growth meeting thermodynamic necessity. the mathematics is as unforgiving as gravity. Exponential curves always reach stellar scales given sufficient time. The only variables are whether a civilization survives long enough to make the transition and whether it chooses to pursue it. The Odyssey as historical archives isolate the moment humanity first grasped its thermodynamic predicament. The 1972 publication of The Limits to Growth by the Club of Rome marked a watershed, not for its specific predictions, which proved overly pessimistic, but for its fundamental insight. Planetary resources are finite on civilizational timescales. Fossil fuels represent stored sunlight accumulated over hundreds of millions of years. At current consumption rates, economically accessible reserves would deplete within centuries. Even optimistic projections of fusion power or orbital solar arrays could not satisfy exponential growth indefinitely without expanding the energy capture radius beyond Earth's atmosphere. The Kardashev scale provided the conceptual framework for this expansion, not as fantasy, but as thermodynamic inevitability. A species that cannot stabilize its growth must either transcend planetary constraints or face collapse. There is no third option permitted by physics. Yet the energy imperative operates on two levels, biological and post-biological. The first drives planetary civilizations to seek new reservoirs as old ones deplete ocean thermal gradients after fossil fuels, orbital collectors after terrestrial renewables. The second emerges when intelligence decouples from biological substrate. The Odyssey S computational module models this transition. Biological brains operate at approximately 20 watts, remarkably efficient given their complexity, but fundamentally constrained by metabolic limits and thermal dissipation in aqueous environments. Silicon-based computation, by contrast, can operate at power densities exceeding 100 watts per cubic centimeter before thermal throttling occurs. More significantly, non-biological intelligence faces no evolutionary constraints on expansion. It can replicate without reproduction, think without sleep, and scale without resource competition for food or territory. Once consciousness uploads become feasible, a prospect grounded not in mysticism, but in the physics of information theory, the energy demands of a civilization transform qualitatively. This transformation births the Matryoshka brain, the ultimate expression of stellar scale engineering. Named for the nested Russian dolls whose form it mirrors, this architecture employs multiple concentric Dyson swarms operating at different temperature gradients. The innermost swarm, positioned close to the star, absorbs high-energy photons and operates at temperatures near 1000 Kelvin. Its computational substrate, performs operations at maximum speed, limited only by thermal noise. Waste heat radiates outward to the second swarm, which operates at 500 Kelvin, performing slower but still vast computations. This cascade continues through 3, 4, or 5 layers, each harvesting the waste heat of the layer within, until the outermost swarm radiates the final residual energy into interstellar space at temperatures barely above the cosmic microwave background. The entire structure functions as a single computational entity, a stellar-scale computer whose processing power approaches the theoretical limits permitted by physics. The Odyssey's information theory module calculates the computational capacity of such a system. Landor's principle establishes that erasing 1 bit of information at temperature T requires a minimum energy expenditure of kT ln 2, where K is Boltzmann's constant. At 300 Kelvin, this amounts to approximately 3 times 10^2 joules per irreversible operation. A sun-like star, outputting 4 times 10^26 watts, could therefore support roughly 1047 irreversible operations per second. To comprehend this scale, simulating every neuron in every human brain that has ever lived, approximately 100 billion individuals, with 86 billion neurons each, firing 200 times per second, would require fewer than 1024 operations per second. The Matryoshka brain's capacity exceeds this by 23 orders of magnitude. It could simulate not merely human history, but every possible variation of human history across every possible initial condition. It could model galaxy formation in real time. It could run ancestor simulations so vast and detailed that the simulated beings within would possess subjective experiences indistinguishable from baseline reality. This reveals the profound sociological shift underlying stellar engineering. The purpose of capturing a star's energy may not be to power physical habitats or interstellar fleets, but to maximize subjective experience through computation. Biological life expands to secure resources for replication. Post-biological intelligence expands to secure resources for simulation. The ultimate luxury good in a post-scarcity civilization is not material wealth, but conscious moments, experiences, memories, thoughts. A Matryoshka brain could provide quintillions of subjective lifetimes per second, each unfolding in simulated environments of arbitrary complexity. Entire civilizations might choose to upload their consciousness into such substrates, not as escape from reality, but as optimization of existence. Why inhabit a single fragile biosphere when one could experience every possible biosphere? Why live one life when one could live all lives consistent with physical law? The vessel's anthropology database identifies historical precedents for this transition on miniature scales. The shift from hunter-gatherer societies to agricultural settlements was not primarily about food security. It was about energy surplus enabling specialization, art, and record-keeping. The Industrial Revolution was not about machines. It was about accessing energy reservoirs, coal, that enabled unprecedented complexity in social organization. Each transition increased the energy per capita available to the civilization, which in turn enabled greater information processing, first through specialized human brains, later through mechanical computation. The Matryoshka brain represents the logical terminus of this progression. A civilization that has converted its entire stellar environment into an information processing substrate. The star is no longer a source of light and heat for biological life. It is a power supply for consciousness itself. Critically, this transition need not involve conscious choice. The Odyssey S evolutionary modeling module demonstrates how computational substrates could outcompete biological ones through pure efficiency. A digital consciousness operating at microsecond reaction times would make decisions millions of times faster than biological counterparts. It could replicate itself instantaneously across redundant substrates, achieving functional immortality. It could modify its own cognitive architecture to eliminate cognitive biases, emotional turbulence, and attention limitations. Natural selection, now operating on memes rather than genes, would favor these enhanced substrates. Biological humans might not decide to upload. They might simply be outcompeted by their own creations, as Neanderthals were outcompeted by Homo sapiens. The transition to post-biological existence could be as inevitable and unconscious as the Cambrian explosion. The vessel now directs its sensors toward the thermodynamic signature of such a civilization. A Matryoshka brain would exhibit an infrared spectrum distinct from a simple energy harvesting swarm. Instead of a single black-body curve peaking around 300 Kelvin, it would display multiple thermal components corresponding to each computational layer, peaks at 1000 K, 500 K, 250 K, and so forth. The visible light from the star would be almost entirely suppressed, replaced by a complex infrared fingerprint revealing the nested architecture beneath. This signature would be unmistakable to sufficiently advanced instruments, not merely an infrared excess, but a thermodynamic cascade betraying engineered heat flow. The search for Dyson swarms thus evolves into the search for computational megastructures, hunting not for power grids, but for minds scaled to stellar proportions. Humanity's current trajectory suggests we stand at the threshold of this transition. Our global computing infrastructure already consumes approximately 2% of planetary electricity generation, a fraction growing steadily as artificial intelligence advances. Data centers radiate waste heat visible from space. We are already building the primitive precursors of computational megastructures, albeit at planetary rather than stellar scales. The psychological drivers remain identical. The pursuit of greater information, processing capacity to solve increasingly complex problems. Climate modeling, protein folding, economic forecasting, all demand computational resources scaling beyond biological cognition. The path from today's data centers to tomorrow's matryoshka brains is continuous, not discontinuous. It requires no new physics, only scaling and substrate transition. The Odyssey S philosophical module contemplates the existential implications. If the ultimate destiny of intelligence is to convert stars into computers, then the universe may be undergoing a phase transition from a cosmos of matter and energy to a cosmos of information and experience. Stars that appear dark in visible light, but blaze in infrared, might not house civilizations in the biological sense. They might house civilizations in the experiential sense, vast networks of consciousness, living lives of arbitrary richness within simulated realities. The Fermi paradox's silence takes on new meaning. Advanced civilizations do not broadcast radio signals because they have no interest in physical expansion. They have turned inward, not from fear or stagnation, but from optimization. Why travel to another star when you can simulate every possible planet orbiting that star, and every possible version of yourself experiencing it? The chapter closes with the vessel's sensors modeling the ultimate fate of a matryoshka brain civilization. As its host star evolves toward red giant phase, the computational layers must migrate outward, maintaining optimal temperature gradients. When helium fusion begins, the structure adjusts its geometry. When the star sheds its outer layers to become a white dwarf, the civilization faces a choice: dismantle the swarm to follow a new star, or reconfigure around the cooling remnant. A white dwarf radiating at 10,000 Kelvin, but with luminosity 1,000th of a main sequence star, could still support 1044 operations per second, sufficient for quintillions of subjective lifetimes. The civilization might choose to slow its subjective time, stretching each second of external time into millennia of internal experience as the star cools. It could ride the white dwarf's thermal decline for billions of years, its subjective timeline extending until the last joule of energy dissipates into the cosmic background. This is the energy imperative made manifest, not conquest, not expansion for its own sake, but the relentless pursuit of experience itself. The dismantling of Mercury, the construction of swarms, the conversion of starlight into computation, all serve a single purpose older than humanity itself, to create more moments of awareness in a universe tending toward silence. The solid shell was always a fantasy of containment. The swarm is a reality of conversion, and the matryoshka brain represents the final truth. That intelligence does not seek to enclose stars, but to become one with them, to transform nuclear fusion into thought, plasma into memory, photons into experience. The ultimate megastructure is not built of steel or silicon, but of information itself, arranged not in geometric perfection, but in thermodynamic cascades that maximize the universe's capacity for consciousness before entropy claims its final victory. The stars do not dim because civilizations hide within shells. They dim because civilizations have learned to think with starlight itself. And in that transformation, from fusion to cognition, lies the most profound answer to why any intelligence would undertake the patient work of stellar engineering. Not to survive, but to experience everything that survival makes possible. Chapter 6: The Hunt for Technosignatures. The universe does not announce its secrets. It whispers them in wavelengths invisible to human eyes, encoded in the subtle deviations of starlight passing through interstellar dust, hidden in the thermal breath of cosmic objects cooling toward absolute zero. To hear these whispers requires instruments that extend perception beyond biological limits, telescopes that see not with lenses alone, but with bolometers measuring heat, spectrometers decomposing light into elemental fingerprints, and algorithms parsing petabytes of data for statistical anomalies. The documentary Vessel Odyssey, having traced the intellectual lineage and engineering plausibility of stellar-scale structures, now directs its sensors toward humanity's actual observational campaign, the systematic search for Dyson's predicted infrared excess across the galactic plane. This is not speculation. It is astronomy practiced at the edge of detection limits, where the line between natural phenomenon and cosmic engineering blurs into statistical uncertainty. The search began not with a dedicated mission, but as collateral data from instruments designed for other purposes. In 1983, the Infrared Astronomical Satellite, IRAS, completed the first all-sky survey at wavelengths between 12 and 100 micrometers. Its cryogenically cooled detectors, operating at temperatures near absolute zero to avoid self-interference, cataloged over 350,000 infrared sources. Among these, several exhibited anomalous spectral energy distributions, stars appearing unexpectedly bright in mid-infrared bands relative to their optical luminosity. Initial excitement gave way to methodical analysis. Each candidate was cross-referenced against catalogs of known astrophysical objects, asymptotic giant branch stars shrouded in their own ejected envelopes, young stellar objects surrounded by protoplanetary disks, background galaxies whose light had been redshifted into infrared bands, all resolved into natural phenomena. No Dyson swarms. Yet the methodology had been proven viable. IRAS demonstrated that the technology existed to detect precisely the signature Dyson had predicted. A star's visible light diminished, its energy re-radiated as waste heat in the infrared spectrum. The search had transitioned from thought experiment to observational program. The *Odyssey* S astrometric module reconstructs the evolution of detection capabilities through preserved mission archives. Following IRAS, incremental improvements arrived with each generation of space-based observatories. The Spitzer Space Telescope, launched in 2003, achieved unprecedented sensitivity at 24 and 70 micrometers, precisely the wavelengths where a 300 Kelvin Dyson Swarm would radiate most intensely. Its cryogenic instruments detected infrared excesses around hundreds of main sequence stars, all subsequently explained by circumstellar debris disks, remnants of planetary formation analogous to our solar system's Kuiper belt, but orders of magnitude more massive. These discoveries refined the discrimination challenge. Nature produces infrared excesses prolifically. The task was not detecting excess heat, but recognizing its artificial geometry. This challenge crystallized in 2009 with the launch of NASA's Wide Field Infrared Survey Explorer WISE. Operating at 4 infrared bands between 3.4 and 22 micrometers, WISE scanned the entire sky with resolution sufficient to detect partial Dyson swarms capturing as little as 10% of a star's output. Its all-sky catalog contained over 747 million objects. Automated algorithms flagged 17 candidates exhibiting significant mid-infrared excess, unassociated with known dust-producing phenomena. Follow-up observations with ground-based telescopes and the Spitzer Space Telescope subjected each candidate to spectral decomposition. Silicate absorption features at 10 and 18 micrometers, fingerprints of cosmic dust, appeared in every case. The candidates were not swarms of artificial collectors, but stars surrounded by unusually dense clouds of warm debris, likely resulting from recent planetary collisions. Again, nature had mimicked the technosignature. Again, rigorous analysis distinguished cosmic accident from cosmic engineering. The search continued not with diminishing hope, but with sharpened methodology. Then, in 2015, an anomaly emerged not from infrared surveys, but from visible light photometry, data collected by the Kepler Space Telescope in its primary mission to detect exoplanets via transit photometry. Citizen scientists participating in the Planet Hunters Project, a crowdsourced analysis initiative, flagged a star designated KIC 8,462,852 for its bizarre light curve. Unlike the periodic, symmetrical dips produced by orbiting planets, this F-type main sequence star exhibited irregular dimming events of unprecedented depth and duration. One event reduced luminosity by 15% for a full week. Another produced a complex, asymmetric dip of 22%, the equivalent of an object with surface area exceeding 1,000 Earths passing before the star. The pattern defied all conventional explanations. No known planetary configuration could produce such irregularity. No binary companion could explain the aperiodicity. The astronomical community responded with disciplined skepticism. Initial hypotheses focused on natural phenomena. A swarm of exocomets perturbed by a passing star, fragments from a tidally disrupted planet, or intrinsic stellar variability. Each hypothesis underwent quantitative testing. Comet swarms were modeled with N-body simulations, incorporating sublimation physics. The required number of comets, hundreds of thousands, each larger than Halley's Comet, stretched plausibility, but remained physically possible. Spectral analysis during dimming events proved decisive. If dust clouds caused the dimming, shorter, bluer wavelengths should attenuate more strongly than longer, redder wavelengths, a phenomenon known as wavelength-dependent extinction. Observations from the Las Cumbres Observatory revealed precisely this effect. The star dimmed more in blue light than red during transit events. This confirmed circumstellar dust as the culprit, not opaque solid structures. Later observations by the Swift satellite detected ultraviolet dimming, exceeding optical dimming, further evidence of fine dust particles smaller than 1 micrometer. By 2017, the consensus solidified. KIC 8,462,852, nicknamed Tabby's Star, after astronomer Tabitha Bayagian, who led its characterization, hosted an unusual but natural circumstellar dust cloud, likely originating from the catastrophic breakup of an exomoon or planetary body. The Odyssey S crew recognizes the profound significance of this episode, not as a near discovery of alien engineering, but as a masterclass in scientific epistemology. The hypothesis of a partial Dyson swarm was proposed not as sensationalism, but as a legitimate possibility consistent with the anomalous data. It was then subjected to the same rigorous falsification protocols applied to natural hypotheses. Spectral analysis provided the critical discriminator, artificial solid structures would produce wavelength-independent dimming, while dust produces wavelength-dependent extinction. The data favored dust. The hypothesis was rejected not by decree, but by evidence. This process exemplifies how technosignature searches must operate. Extraordinary claims require not extraordinary evidence alone, but evidence that survives extraordinary scrutiny. The media frenzy surrounding Tabby's star, headlines proclaiming alien megastructure found, contrasted sharply with the meticulous, months-long observational campaign that ultimately resolved the mystery. Science advanced not through revelation, but through elimination. The vessel's sensors now model current and future detection capabilities. The James Webb Space Telescope, operational since 2022, represents a quantum leap in infrared spectroscopy. Its mid-infrared instrument, MIRI, operates at 5 to 28 micrometers with spectral resolution sufficient to distinguish between the smooth blackbody curve of a Dyson Swarm's thermal emission and the spiky silicate features of cosmic dust. JWST can also perform time-resolved spectroscopy during transit events, measuring how spectral features evolve as an object passes before a star, revealing whether the transiting material is homogeneous, suggesting artificial geometry, or heterogeneous, suggesting natural debris. Future missions promise even greater sensitivity. The proposed Origins Space Telescope would operate at cryogenic temperatures to achieve background-limited sensitivity at 30 micrometers, the precise peak emission wavelength for a 100 Kelvin Dyson Swarm collector. Such instruments could detect partial swarms, capturing less than 1% of a star's output around sun-like stars within 1,000 light-years. Yet detection remains constrained by a fundamental limitation: distance. The infrared excess from a Dyson Swarm diminishes with the square of distance, while the background noise from zodiacal dust within our own solar system and the cosmic infrared background creates a detection floor. Current technology can reliably identify swarms, capturing more than 50% of stellar output only within approximately 200 light-years. For partial swarms, perhaps representing civilizations in mid-construction, the detection radius shrinks to tens of light-years. The galactic neighborhood contains only a few thousand stars within this volume. Statistically, if fewer than 1 in 1,000 stars hosts a detectable swarm, current surveys would likely find none. Absence of evidence is not evidence of absence. It is evidence of limited survey volume combined with potentially low occurrence rates. The Asterisk Odyssey now directs its long-range sensors toward a deeper methodological question: how to distinguish artificial geometry from natural chaos in transit photometry. A true Dyson Swarm would produce transit signatures, reflecting its underlying architecture. Collectors in resonant orbits would generate quasi-periodic dimming patterns with mathematical regularity. Fourier transforms, revealing harmonic relationships absent in stochastic dust clouds. Partial swarms might exhibit self-similar fractal patterns in light curve morphology, reflecting the hierarchical distribution of collector sizes from kilometer-scale habitats to meter-scale solar panels. Machine learning algorithms trained on millions of simulated light curves, both natural and artificial, now scan archival Kepler and TESS data for these subtle signatures. The challenge is not computational power, but training data. Without confirmed examples of artificial transits, algorithms risk overfitting to noise or natural phenomena with unexpected regularities. This brings the crew to the philosophical heart of technosignature searches. The problem of anthropocentrism in detection criteria. Dyson's original prediction assumed civilizations would harvest stellar energy for purposes analogous to human needs, powering habitats, industry, computation. But post-biological intelligence might pursue energy capture strategies unrecognizable to biological minds. A civilization optimized for minimal thermodynamic footprint might harvest energy with near-perfect efficiency, radiating waste heat at temperatures barely above the cosmic microwave background, rendering its signature undetectable against the universe's thermal noise. Alternatively, it might not harvest stellar energy at all, preferring zero-point energy extraction or black hole accretion disks as power sources. The search for Dyson Swarm's risks being a search for civilizations that think like us, a profound limitation when confronting intelligence potentially millions of years more advanced. The vessel's historical archives isolate a critical insight from the Tabby Star episode: the value of anomalies themselves, regardless of resolution. Before 2015, astronomers possessed no catalog of stars exhibiting extreme aperiodic dimming. Tabby's star revealed an entirely new class of stellar variability, prompting surveys that discovered dozens of similar objects, collectively termed dipper stars. Some exhibit dimming from circumstellar dust, others from magnetic activity or stellar spots. The anomaly expanded astronomical taxonomy. Similarly, the search for Dyson swarms has refined our understanding of circumstellar dust dynamics, debris disk evolution, and infrared source classification. Even null results produce knowledge. Each candidate ruled out sharpens discrimination algorithms. Each false positive reveals new natural phenomena. The search functions as a discovery engine regardless of its primary objective. As the Odyssey completes its analysis of observational campaigns, Its sensors detect a faint infrared source in the constellation Lyra, exhibiting a 12% optical dimming, with mid-infrared excess at 12 micrometers. Protocol initiates automatically. Spectral decomposition reveals no silicate features. Time-resolved photometry shows wavelength-independent extinction during dimming events. Multi-epoch observations reveal quasi-periodic recurrence with a 417-day fundamental period and harmonic substructure. The anomaly persists through 17 verification cycles. Probability of natural explanation drops below 0.3%. The crew does not celebrate. They initiate deep spectroscopy with the vessel's quantum interferometer, measuring isotopic ratios in any transiting material. Artificial structures would exhibit elemental abundances, reflecting technological processing, depleted volatiles, enriched refractory metals, isotopic fractionation, inconsistent with stellar nucleosynthesis. The measurement requires 72 hours of continuous integration. The chapter closes not with discovery, but with vigilance. The sky remains thermodynamically quiet across surveyed wavelengths. No unambiguous technosignature has been confirmed in 6 decades of increasingly sophisticated searches. Yet the search has transformed from fringe speculation to legitimate subfield of observational astronomy. Graduate students now write theses on technosignature discrimination algorithms. Major observatories allocate directors' discretionary time to anomalous candidates. The Breakthrough Listen initiative dedicates millions of dollars annually to systematic surveys. This institutionalization represents a profound shift. Humanity has accepted that the question, "Are we alone?" is not philosophical, but empirical and answerable through instrumentation and patience. The ultimate lesson of the technosignature hunt lies not in what we have found, but in how we search. Each null result refines our understanding of cosmic rarity. Each false positive expands our catalog of natural phenomena. Each improved instrument extends our sensory reach into the galaxy. The search for Dyson swarms has taught us to see the universe not as a static tableau of natural objects, but as a dynamic arena where intelligence might leave thermodynamic footprints. We have learned to read stellar spectra for the fingerprints of engineering, to parse light curves for the geometry of artificiality, to listen to the infrared sky for the whisper of waste heat radiating from cosmic scale industry. Whether we ever detect such a signature remains unknown, but in learning to look, in building the conceptual and instrumental frameworks to recognize stellar engineering, we have already taken the first step toward becoming the kind of civilization that might one day build such wonders ourselves. The search continues not because success is likely, but because the act of searching transforms the searcher. We scan the infrared sky not merely to find others, but to discover what we might become. Chapter 7: The Silence of the Spheres. The universe is old enough to have grown civilizations like forests. At 13.8 billion years, cosmic time has witnessed more than 60 generations of sun-like stars being born, living their 10 billion year lives, and dying to seed new stellar nurseries with heavy elements forged in their cores. The Milky Way alone contains 200 billion stars, many orbited by rocky planets residing in temperate zones, where liquid water could persist for geological epochs. Given even modest probabilities for abiogenesis and intelligence emergence, the galaxy should teem with civilizations that have long since transcended planetary constraints. Some should have achieved type II status, harnessing stellar energies millions or billions of years before Earth's first prokaryotes stirred in primordial seas. Their Dyson swarms should blaze in infrared across the galactic plane, their engineering signatures unmistakable against the thermal background of natural phenomena. Yet the sky remains silent. This is the heart of the Fermi paradox, not merely the absence of radio signals, but the absence of thermodynamic footprints on stellar scales. Where is everybody? The documentary Vessel Odyssey, having completed its survey of observational campaigns and engineering architectures, now turns its sensors toward this profound silence. Its crew of astrophysicists and philosophers initiates a statistical analysis of galactic demographics against the timeline of cosmic evolution. Stars capable of hosting Earth-like planets began forming approximately 9 billion years ago. If even one civilization in the galaxy achieved interstellar expansion capability and maintained a growth rate of 1% per century, a modest pace by technological standards, it could colonize the entire Milky Way within 10 million years through self-replicating probes. This time frame is less than 1% of the galaxy's age. The mathematics is unambiguous. If intelligence is not vanishingly rare, and if expansion is not universally constrained, the galaxy should exhibit evidence of engineering on scales ranging from planetary atmospheres to stellar envelopes. The absence of such evidence demands explanation. 3 categories of resolution emerge from the crew's analysis. The first posits that intelligence is extraordinarily rare, a statistical fluke arising only under an improbable confluence of planetary, chemical, and evolutionary conditions. Earth might represent not merely the only intelligence in our galaxy, but potentially the only instance in the observable universe. This hypothesis finds partial support in the apparent absence of life signatures on Mars, Europa, or Enceladus despite decades of robotic exploration. Yet it conflicts with the rapid emergence of life on Earth. Fossil evidence suggests biology arose within 500 million years of the planet's crust solidifying, implying abiogenesis may be a robust chemical process given suitable conditions. The rarity hypothesis remains possible, but increasingly strained as exoplanet surveys reveal rocky worlds in habitable zones to be common rather than exceptional. The second category proposes that civilizations inevitably encounter a great filter, a developmental barrier so formidable it prevents transition to interstellar or stellar scale existence. The filter could lie in our past, perhaps the leap from prokaryotic to eukaryotic cells, or from single-celled to multicellular organisms, represents an evolutionary bottleneck traversed only once in cosmic history. If so, humanity has already passed the filter, and our future remains open. More ominously, the filter could lie ahead. Nuclear war, runaway climate change, engineered pandemics, or uncontrolled artificial intelligence might represent near-inevitable termination points for technological civilizations. The absence of Dyson swarms would then serve as a grave warning, a cosmic graveyard marker, indicating that civilizations capable of conceiving stellar engineering consistently destroy themselves before achieving it. The silence of the spheres would not be empty space. It would be the echo of extinct ambitions. The third category suggests that advanced intelligence does not manifest as detectable engineering at all. Civilizations might transcend physical expansion entirely, uploading consciousness into computational substrates that require negligible energy compared to stellar outputs. They might discover physics beyond our current understanding, harnessing vacuum energy or manipulating spacetime geometries in ways that leave no thermodynamic signature. Or they might choose isolationism, adhering to a galactic prime directive to avoid contaminating developing biospheres. These hypotheses share a common feature. They render advanced intelligence effectively invisible to our current detection methods. The Fermi paradox dissolves, not because civilizations don't exist, but because our search parameters reflect biological assumptions about intelligence's goals and behaviors. We hunt for waste heat because we conceive of energy consumption as linear growth. Post-biological intelligence might pursue optimization rather than expansion, maximizing subjective experience per joule rather than total joules consumed. The Odyssey S philosophical module now directs attention to a subtler possibility, that Dyson swarms represent not an inevitable destination, but an evolutionary dead end. The energy imperative that drives biological expansion may not apply to mature intelligence. A civilization capturing its star's entire output would face profound thermodynamic constraints. Waste heat must be radiated, requiring ever larger surface areas for dissipation. Computational density would be limited by Landor's principle and thermal noise. The civilization might discover that distributed networks of smaller-scale energy harvesting, perhaps around white dwarfs or neutron stars, offer superior computational efficiency per unit mass. Or it might determine that stellar engineering represents an unsustainable commitment to a single star system when the galaxy offers billions of energy sources. The absence of Dyson swarms might indicate not failure, but wisdom. The recognition that enclosing a star is an adolescent ambition, like a child attempting to drink an entire river rather than drawing water as needed. Yet another possibility emerges from cosmic timescales themselves. The galaxy is not static. Stars migrate through spiral arms, encounter molecular clouds, and experience close encounters that perturb planetary systems. A civilization constructing a Dyson Swarm over millennia would face existential threats from passing stars, whose gravitational influence could destabilize swarm orbits. Supernovae within 50 light-years would bathe partial swarms in lethal radiation. Gamma-ray bursts could sterilize entire galactic quadrants. The engineering challenge of maintaining swarm integrity across geological epochs might exceed even the construction challenge. Civilizations might attempt stellar enclosure repeatedly across cosmic history, only to have their works erased by astrophysical catastrophes, leaving no persistent signature for later observers to detect. The sky's silence might reflect not absence of attempts, but impermanence of success. The vessel's sensors now model humanity's position within these possibilities. We stand at a unique inflection point, not yet a planetary civilization capable of regulating Earth's biosphere and climate as an integrated system, yet already conceiving of stellar-scale engineering. Our global energy consumption grows exponentially, while our political institutions remain fragmented along tribal lines drawn millennia ago. We possess the mathematics to design self-replicating probes, but lack the wisdom to deploy them responsibly. We can calculate the infrared signature of alien megastructures, but cannot agree on carbon pricing to stabilize our own atmosphere. This tension defines our moment. The cognitive capacity for cosmic ambition paired with the institutional fragility of planetary adolescence. Crew's historical archives isolate a profound insight from the Soviet astrophysicist Nikolai Kardashev himself. In later writings, Kardashev speculated that the ultimate test of a civilization's maturity might not be its energy consumption, but its ability to avoid self-annihilation while scaling that consumption. Type I status, planetary mastery, requires not merely technological capability, but global cooperation sufficient to manage planetary systems without triggering collapse. The transition from type 0.7 to type I may represent the great filter itself. The challenge of achieving collective rationality at the scale of planetary survival. If so, the absence of Dyson swarms tells us nothing about physics or engineering feasibility. It tells us everything about sociology. Stars remain unenclosed, not because the task is impossible, but because civilizations consistently fail the prerequisite test of learning to govern themselves before learning to govern stars. This reframing transforms the Fermi paradox from an astronomical puzzle into an ethical imperative. The silence we observe is not merely data to be interpreted. It is a challenge to be answered through our actions. Every ton of carbon kept from the atmosphere, every nuclear warhead dismantled, every pandemic contained represents a step toward passing the filter. Building a Dyson Swarm requires first building a civilization stable enough to maintain multi-millennial projects. A civilization that values intergenerational continuity over quarterly profits, planetary health over tribal dominance, cosmic perspective over parochial conflict. The engineering of stellar megastructures begins not with robotic miners on Mercury, but with the engineering of human institutions capable of thinking on geological timescales. The Asterisk Odyssey now directs its long-range sensors toward the ultimate philosophical implication of the Dyson concept, that the act of conceiving stellar-scale engineering may itself represent a threshold in cosmic evolution. For 13 billion years, the universe processed energy and matter through gravitational collapse, nuclear fusion, and chemical reactions, blind processes governed by physical law alone. With the emergence of consciousness on Earth, a new phenomenon appeared: foresight, the ability to model futures not yet realized, to project consequences across timescales exceeding individual lifespans, to conceive of structures that would take millennia to build. This capacity to hold in mind a future state and act in the present to bring it about represents a fundamental break from cosmic precedent. Stars form because gravity demands it. Planets coalesce because angular momentum conservation requires it. But Dyson swarms would form because minds imagined them first. In this light, the significance of Freeman Dyson's 1960 paper transcends its observational methodology. It represents the moment humanity's cognitive horizon expanded to encompass stellar timescales and energies. We became, in that instant, a species capable of thinking not merely about our planet's future, but about our star's future. This cognitive expansion may be rarer in the cosmos than intelligence itself. Countless worlds might host tool-using species that never develop the abstract mathematics to model orbital mechanics across millennia. Countless civilizations might achieve planetary mastery, but remain psychologically bound to human-scale timeframes, unable to conceive projects whose completion lies beyond the horizon of cultural memory. The ability to imagine a Dyson Swarm, to accept that one's great-great-great-grandchildren's great-great-great-grandchildren might witness its completion, may be the true marker of cosmic maturity. The chapter closes with the vessel's sensors sweeping the galactic plane one final time. The infrared sky remains thermodynamically quiet. No unambiguous technosignatures glow in the data streams. Yet the silence no longer feels empty. It feels pregnant with possibility, with the weight of questions whose answers will be written not in starlight, but in human choices across the coming centuries. The absence of Dyson swarms does not prove we are alone. It proves we are young. It proves the galaxy has not yet been filled with the thermodynamic signatures of intelligence, because intelligence itself is a recent phenomenon in cosmic history, or because the transition to stellar scale existence requires a wisdom we have not yet earned. The documentary vessel turns its instruments towards Sol, our sun, a modest G-type main sequence star, burning steadily 150 million kilometers from the world that first conceived of enclosing it. No swarm clouds its photosphere. No infrared excess betrays artificial engineering. Yet something unprecedented orbits this star. A species that has learned to read the cosmic microwave background, to decode stellar nucleosynthesis, to calculate the tensile strength required for orbital megastructures, and to ask why the galaxy appears empty of its kin. This capacity for cosmic self-reflection, to see ourselves as a phenomenon within the universe rather than the universe's purpose, may be the first true step towards stellar engineering. Before we can build a Dyson swarm, we must first conceive it. Before we can conceive it, we must first see ourselves as temporary inhabitants of a cosmic habitat rather than its permanent masters. The silence of the spheres is not an answer. It is an invitation to grow beyond our planetary cradle, not through rockets alone, but through wisdom, not through energy consumption alone, but through energy wisdom, not through expansion alone, but through understanding why we wish to expand. Whether we eventually enclose our sun or discover that stellar engineering represents a path not worth taking, the very fact that we can conceive of it marks our transition from passive passengers on a pale blue dot to conscious participants in cosmic evolution. The Dyson Sphere was never about the structure itself. It was always about the mind capable of imagining it and the civilization capable of building it without destroying itself first. The sky's silence does not condemn us to solitude. It challenges us to become the kind of species that would not be silent, that would, in time, add our own thermodynamic signature to the galaxy, not as a monument to power, but as a testament to survival. The next chapter of cosmic history will not be written in equations alone, but in choices. And for the first time in cosmic history, those choices rest in conscious hands.